So as always, it's a pleasure to see you again. Sorry for interrupting your discussion. It's 2:10, so maybe we have to start. We're going to be discussing about interrupts today, which is an alternative way of asking devices whether they completed the job we asked them to do or whether there is something for us that needs attention. Just to remind you, last time we talked about UART, and we said that if we want to send a character, we have to go and poll it. That is, say, can we please send a character? You can say whether it has space or not, whether it's busy or not. And when it's not busy, we can actually send the character. By the way, if we want to receive a character again, we have to go and ask it, is there a character for me to receive? Okay. So I want you to envision a little bit a system where, for example, your mouse, the thing you use to move your cursor, is connected to a serial port, and you have to use polling. That is, somehow you have to write any program out there, say this is like a graphical interface, so that every so often it goes and asks to the mouse, did you actually move? And let me draw this. Did you move? Oh, let me draw this. But you have to do this programmatically. That's it. You have to keep asking while also writing your own program. And this has to be embedded in your code. I hope you understand this becomes pretty unmanageable after a while. And if you think this is going to be maybe a computer that has a network, maybe while you're asking the mouse, did you move? Then after a while, you have to ask the network card, do you have a packet for me? Or can I send a packet? And any kind of I/O device, if you're playing audio samples, for example, you have to go to the audio device and say, oh, did you play the previous sample? Can I send another one? So you can, very quickly, you end up with a problem that's pretty much untracked. You cannot solve it. It becomes too complicated. Everything has to be part of your program. Okay. So there is an alternate way, which is equivalent in real life, where you say to somebody, you know what? I am here. I'm sitting on this desk. If you want my attention, come find me. So, for example, if you have a device like the UART where it receives characters, the device will have a way to go to the CPU and it says, hi, CPU, I have a character if you want it. So it has an ability of going and knocking on the door and says, I'm here. There is something for you. The CPU can make a decision whether to handle it or not. That frees the CPU and all your programs from dealing with asking the UART whether it has a character or not. When it does, it will come knock on your door and say, I do. Similarly, if you want to send a character, rather than keep asking, can I, you can have an agreement with the UART to say the following. You know what? When you're available to send a character, let me know, because I might have one to send you. Fair enough? So somehow, we need a way for the CPU to be doing its own work, so it's executing your own program. But somehow, we want to stop it for temporarily, knock on its door and say, hi, do this for me. The way this is going to be done is as follows. So let's pretend that this line represents instructions executing. So this is time in a way. I'm executing that instruction, that instruction, that instruction, that instruction, that instruction. At some point, somebody comes, knocks on my door. So I need a mechanism to notify the CPU. This stands for Central Processing Unit. It's another way people refer to processors. So somebody, like a device, the UART, for example, will come and notify the CPU somehow that, you know what, I need you to stop what you're doing for the time being and pay attention to me. So what's going to happen then is, in reaction to that, the CPU will self-induce a call to another piece of code. So this is your own program. When the CPU gets notified that an I/O device needs attention, so some I/O device notifies the CPU will self-induce a call to a piece of code. So it will make the equivalent of a call to some pre-specified function whose job is to talk to the device and say, what do you want from me? Why are you knocking on my door? That's called an interrupt. And the piece of code you're running is called an interrupt handler, which is a very descriptive name because its job is to handle the interrupt request. After the interrupt handler has done processing the request, for example, in the case of UART, it might be, here's the character, or I got the character, I put in some buffer in memory. Then it will return back to the call, and execution will resume for wherever it stopped. So This is your program running. At any arbitrary program position, you're executing instructions, you don't know when, you may get a knock on the door. You decide to respond to that knock on the door because you're a CPU. That corresponds to you're going to make a call to an interrupt handler. That interrupt handler is going to go and respond to the door, which is going to talk to the device that's asking. It's going to handle that request, and then you're going to resume as if nothing happened. Okay? What is important here is to note that this point where you interrupt your normal flow of execution can be any. You're executing any piece of code. You wrote your own function, whatever, your own algorithm, whatever. It's executing gazillions of instructions. At any arbitrary point, somebody may come and request an interrupt. That will be handled according to your instructions. Am I making any sense? We're going to make it very specific now because it's good to talk in the abstract. We're going to make it very specific to Neos 2 and how the UART does this. Fair enough? Okay, so there's a bunch of requirements here that we need to explain, to discuss. Different devices, different CPUs have different ways of doing that. Let's see how Neos does that. So the first requirement is knock on the door. Okay. Again, this is a physical analogy. There's no such thing inside the computer. Everything has to be done with zeros and ones. Somehow we need to have some way of interrupting the CPU or notifying it. So first question is, how does the I/O device knocks on the door? That is, request an interrupt. How does it do that? Okay. Now, in Neos, and pretty much most devices out there, if not all, and most I'm just trying to be careful here, but virtually all of them, the interrupt request is a physical action that happens through dedicated communication channels. What I'm trying to say is the following. Somehow you have a silicon device that's your Neos, right? That's your Neos 2. Right? There's going to be at least one wire coming into Neos, which is called interrupt request wire, IRQ. That in steady state, in the beginning of time, that is, for example, 0. If at any point that wire value goes to 1, VDD, Neos interprets that as somebody knocking on the door. That's what it is. Right? So it's a physical action that a device has to make. Neos in particular has 32 of those. It has IRQ 0 to IRQ 31. If you ever had the pleasure of trying to do anything semi-real time with a Windows PC or Linux, you're going to see that the word IRQ pops up. I mean, this is legacy stuff. There is initially there were like 7 or 8 interrupt request lines on the original CPU. They're still there, plus some more. And you have to deal with that because real-time devices will be sending requests and your CPU has to service them. In particular, if you play with audio with Windows 10, real-time stuff, you're going to see it's a bit challenging to make sure that you don't get popping sounds and stuff like that. Okay. So far, so good. So there are 32 lines in Neos. There is no priority enforced among them. That is, if anybody requests, you're going to be getting some information that says, these are the ones that are requesting, you deal with it. The other CPUs enforce priority among them. That is, if you have multiple devices requesting, you will get some notification that this is the most important device. Deal with this first. The hardware is going to do that for you. For Neos, this is done all in software. Maybe this is a little known fact to some of you. Every PC out there that has a power supply, so every one of them, the power supply itself is connected to one of the IRQ lines on your PC. And when power goes off, because there's capacitance and inductance inside your power supply, the power supply is supposed to be able to say, well, I'm going to have power for a few milliseconds more. But it knows that the power has been disconnected. So it sends a signal to the CPU that says, you know what? We're going down. Do something about it. Well, there's very little you can do, but there is such a thing. That's called, in the case of PC, this is called a non-maskable interrupt, which is like life or death. You got to deal with this now, right? That's what it is. Neos doesn't have any of that. It's the IQ lines, everything is being treated as equal. Okay. So far, so good. So this is how we require the CPU, the device notifies the CPU that it wants to be heard. As in real life, the CPU is like a royalty. It's like a person that's sitting on the desk and says, okay, you can keep knocking on the door. I am going to decide whether I'm going to talk to you or not. So we need a way for the CPU to say, you know what? I'm listening to you. This is called interrupt acknowledgement. And this is a CPU to device action. The previous one is device to CPU. Device says, I want to talk to you. CPU eventually has to go to the device and say, I'm talking to you. Now, in the case of news, this has been done through software. In the interrupt handler. That is, if the CPU decides to respond to the interrupt, it's going to take this action, do a call to the interrupt handler, and because you're going to have to write that interrupt handler, you better have code there that says, goes to the device and says, I am listening. We're going to see that in the case of UART. So it's a combination of hardware. The hardware induces the call to the interrupt handler, and the interrupt handler, this is your responsibility now, not the hardware's responsibility, is supposed to have instructions that goes, find out which is the device that asks for the interrupt, because there are 32 wires, and then says to the device, I got your back, I'm listening to you. So it's a combination of software and hardware. In some other CPUs, that's purely hardware. That is, the moment the CPU does, there is a wire that goes back that's called interrupt acknowledgement, and the CPU raises that and says, I'm talking to you. So you don't have to write instructions for that. The moment you're taking the interrupt and you do the call, the hardware does it for you. Making sense? All right. Then you have to handle the interrupt. And in EOS, all of this is instructions. Okay. And eventually you have to return back to the code. So 3, handle the interrupt. This is all software. It's device specific. For every device, you have to run your own interrupt handler. You must know what you're doing. To do that, you have got to read the manual and do the right thing. Okay? And then 4, you got to return to the code. A better way to say that might have been to say resume normal execution, as if nothing happened. Now, around this, we got to make sure that this is pretty much invisible to your code. That is, notice, I am happily executing my program. I'm using some registers I don't care. I'm using some memory. Some of them I do care, some of them I don't. Okay? This could be anything. Right? This could happen at any arbitrary point. Who is the one that knows who is using what? I am. That I wrote this program. So the interrupt handler must be written in a way that can assume virtually nothing about your code. It has to be done in a way that pretty much preserves everything. There is only some agreement, which is basically there's only one register that it can change in the beginning. And then it has to find a way, if anything, it will touch anything, then it has to preserve it. And the way this is going to be done is through the stack. Okay, I'm going to explain that. So preserve. What memory locations you're going to be able to touch is done by agreement. So the software says, you know, don't touch these memories because they're used by the interrupt handler. You can use some other ones. That's done statically. So every program knows not to touch those locations. Registers, well, it has to be done by the interrupt handler. And the way we're going to save registers is through the stack. Okay. All right, all of this is very abstract. Let's try to make it very, very specific. Okay. What is the sequence in EOS? 1, device asserts IRQ, some IRQ. In the case of UART, it might be 8. Why is it 8? Favorite answer, because somebody decided it's going to be 8. Yes? IRQ is the wire. It's an actual wire. It's a physical connection. So somebody went and put that there. Okay. He had 32, he said, okay, 8 looks like the one for me. UART goes there. That is the communication mechanism for the device to say, hello, CPU, talk to me. Okay, that's what it is. It's supposed to be the device raises the voltage on that wire, The CPU is designed so that it listens to that they're looking for attention. Okay? Now, assuming the CPU wants to grant the request, what it does the following. There are some registers involved here. They are called control registers. First thing it does, it takes the control register 0 and copy to control register 1. For the time being, just take it as it is. Okay. I'll explain later on what happens, right? Now, let me remember this. I cannot find it. I'll find it later on in my notes. Sorry for that. I'm trying to remember which bit it is. I should have remembered that. I forgot. Okay. Now, what is important here is the following. That in control register 0, and I'll explain how you can manage those registers, how you can read and write them. Bit 0 is the master switch for interrupts. If that value is 0, the CPU is doing that anytime a device talks to it, blah, 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 blah. So it's not listening to it. Only if this is 1, interrupts are enabled. What this thing is supposed to read is serviced. Okay. So it's a master switch. It's like the CPU will listen to you. Okay. Now, what NEOS does in response to an interrupt, it copies this to control register 1, so it makes a copy of it, and then it does the following. Control 0, bit 0 equals 0. That is, the moment NEOS decides to grant an interrupt request, it freezes any subsequent request for the time being, because there are some steps that I need to complete before it can handle anything else. I'll explain later on why this is absolutely necessary. Okay. So in response to, first of all, NEOS does the following. It says, is this bit 0? If it is, I'm not listening to you. I'm not going to respond to your request. You can keep knocking on my door. I don't care. If this is 1, it will take the request. The moment it decides to do that, it makes a copy of this register into another one, and then stops listening to any further requests. It says, I'm going to handle this now. So far, so good? Next thing it does the following. It says, EA, which is an alias for register, I think is R29. Don't quote me on this, but I think it's R29. It's some register. It does EA equals PC plus 4. PC is the instruction address. It's the address of the instruction that will have executed. Remember, I'm executing my code. At some point, somebody knocks on the door. What NEOS does, it finishes executing the instruction that was executed at this point. In between the instruction that just finished and starting the next one, it goes and says, I'm going to handle the interrupt. What it does, though, is does PC equals PC plus 4. So it keeps the address, not of the instruction that we have executed, the instruction after it in memory. That's the definition. Again, when we do the actual design, we'll see why they actually do that, because it simplifies the hardware. But remember, we haven't executed the instruction at PC. So when we return, we have to return to PC minus 4, because we haven't done that instruction. So far, so good? And then it does what is that magical address? That is the location in memory which contains the first instruction of the interrupt handler. Why is it 20? Favorite answer. Because somebody said it's going to be 20. For NEOS, all interrupts are supposed to be handled by one interrupt handler. So it's going to be spaghetti code after a while if you have to deal with many devices. But that's how it's done in NEOS. In other devices, there is usually different addresses depending on who's asking. It's done by hardware. In x86 in particular, there's a table in the beginning of memory that says if you ask, if IRQ 0 is asking, this is where you should go. If IRQ is asking, that's where you should go. This is done all by hardware. NEOS is very simple. Just goes to 20. Yeah.
And what's EA?
It's a register. And it stands for exception address. So depending on which book you read, people use different terms to refer to the same thing. So some people refer to interrupts as interrupts. Some people refer to interrupts as exceptions. And others are using different terms. So in this lecture, I'm going to use the term exception and interrupt to be synonymous to a device asking for an interrupt. Okay. Are we okay? All right. Now, this is the sequence from the CPU. Now you have the interrupt handler running. And that thing is going to do the following. Save any registers. And where? On the stack. So it's going to allocate space on the stack, save any registers it made change. Handle the interrupt. Restore registers. EA equals EA minus 4. And then there is a special instruction that's called ERET, which is return from exception. Okay? What ERET does, it does the following. Control 0 is control 1. So the copy we made here gets copied back to control 0. So control 0 gets returned to the original form. And then PC equals EA. So it's like a return. The only difference is it doesn't use RA. It uses a different register, EA. And on top of that, it affects one of the control registers.
In step 2, EA is equal to PC plus 4.
Yes.
And then in step 4, EA is equal to EA minus 4.
Yes.
Like, why? Like, isn't that just kind of redundant? You're just getting EA back to PC.
Yes, because I didn't execute that instruction.
Okay.
That PC plus 4 is like saying, an interrupt came. I knew I had to execute the instruction at PC. However, though, by the time I have realized that and I update the EA, I have actually incremented PC for whatever reason. Don't ask why. That's what the hardware does. So it writes PC plus 4 there.
Okay.
So, but you should have executed the instruction at PC.
But you didn't. That's not an instruction, right? Like
This is the address of the instruction.
You don't say like EA equals, or PC, or no, sorry.
It's the address. Addresses of instructions, not instructions. If you mean opcodes, no, they're not opcodes, they're instructions. Okay, I've lost you.
But we're not actually writing that instruction.
No. This is like an array, right? But I don't think I've answered your question first. Let's go back to this. So let's say I'm executing some code, right? There is an add instruction, and this is location 100. After that, there is another one, which is 104. Let's say this is a multiply. Then there is another one, 108, which is, I don't know, a shift right logical immediate. And then there is another one, 0C, which is a branch, whatever, okay? Now, interrupts may happen at any point. So let's say the interrupt happens here while this guy is executing. What Niels is going to do is going to execute that fully. And then in between these two, is going to do the following. CTL1 equals CTL0, okay? CTL0 bit 0 equals 0, okay? And then EA equals notice that I should have executed 104. However, the value I will get in EA is not 104, it's 108. Okay? Now, there are two ways you can approach that. You can be eager to understand why, or you can say, okay, that's the way it is, I'm going to deal with it. Okay? It's like as if somebody made one more step, they shouldn't have done that, but they tell you, oops, I did that, please take it back. So that's what we're doing. When we return back, we say, you know what? You gave me 108, but I know you meant to execute 104, so minus 4. Okay? And, huh? No, this is a feature, and it's a well-thought feature. When we design the CPU, you're going to see when they try to implement some performance enhancements, you will try to do some things as early as possible, right? And you're going to see that very early on in the instruction execution, the machine increments the PC. By the way, this bears some similarity to the branches calculating if the address is taken or not taken. There's always a PC plus 4. This is not taken, PC plus 4 plus some offset. Remember that? In either case, there's this PC plus 4. That should be an extra hint that the machine always does that step very early. So it's a design decision. There is some thought behind it. It's a very good decision for what they were aiming for the CPU for. it just simplifies hardware. Sometimes it takes a lot less effort to just write something on a piece of page rather than design the hardware to make this logical. I mean, you can deal with that, right? Just add one more instruction, we're done. That's the idea here. They're simplifying the hardware, and they're making some performance optimizations possible by doing this and telling you about it.
So when you go back to that instruction, like the 0x104,
Yeah.
how do you make sure that you don't execute the instruction after that twice? Like, because after you execute...
Why would have you executed twice? Sorry.
Because after you execute that, where does the PC go to? Is it...
Well, right now PC is 104, right? What's the instruction multiply? What will the CPU do? CPU has no memory of the events that made it arrive at some point. It just knows, here's the PC, I'm fetching that. That's another thing I didn't make it clear. You remember you wake up one morning, you're a CPU, right? How's life? Well, it's an infinite loop. And by the way, if you remember, there's nothing between iterations that crosses other than register values and memory state, right? So when the PC returns back to 104, I'm just executing 104. What will I do after that? 108. Why would it be otherwise? Does that help you or no?
Because we did 108 before we did 104.
No, we didn't.
We did.
What's the sequence of events? In the beginning, there was nothing. You were executing 100, okay? An interrupt came. You said, let me finish with 100. Let's go execute the interrupt 100. Notice I didn't say 104. I didn't say 108. What do I do as bookkeeping before I go to the interrupt handler? I say, interrupt handler, by the way, you start me, and when you start me, the PC plus 4 happened to be 108. That's what the CPU has done. Hasn't executed that, hasn't executed that. It just stopped there and said, let's do this, but by the way, remember that you have to come back here. And rather than saying come back here, it says, this is it. But you know, -4 is where you should come back. It's like a code word thing.
So when you do step 2 and you put PC plus 4 into EA? Or
It's all done by the hardware.
So
This is
you just put PC into EA?
PC plus 4.
Okay.
That's what the hardware does. You don't do that.
You don't do that.
The hardware does that. That's the way machine behaves.
And then in the end, do you do EA minus 4?
You have to do that.
Okay, so you do EA minus 4.
This is instruction. You have to do as a programmer.
ERED, you return that, and then the machine puts EA back into PC.
That's what ERET does.
Okay.
This is exactly what the definition of ERET is. Okay? It's like a return. It doesn't touch RA. It's R31. It touches EA. I think it's 29, but don't quote me on that. And on top of that, copies back CTL1 to CTL0, so restore CTL0. Okay? I don't think we have enough information to appreciate why this is happening right now. Just take it as it is. Okay? So far, so good? All right. So now there is a long and tedious example where we're going to have to find a way to illustrate how to write any interrupt handler. The example I have in my notes, and this is what I plan to do, is the following scenario. We're going to write, first of all, our program is going to be doing the following. There's going to be a value in memory that represents a character. Okay? Characters in CPUs in the old days were 8-bit values. In the beginning, were actually 7 bits, 8 bits. And there is a standard, which I think is called ASCII. No, I know it's called ASCII. Maybe I'm missing some consonants there or whatever. American standard for something, character, blah, 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 blah. All you need to know about this is that there is a table somewhere you can find it. Some interesting numerical properties of that is that the character space is at location 32. And if you try to do a put character to a terminal and say display 32 as a character, you're gonna get a space, empty space, right? Also, I don't remember, but I think 48 is the character 0. 1 is the character 49, so on and so forth. I don't remember the rest, but I think A, small or capital, is 65. B would be the next one, 66. Don't quote me on these specific ones. And the same apply to the capital, but they're different characters. And they go up to 127, 7 bits, the original machines, right? This is the time where machines were predominantly created in English-speaking countries, right? And nobody could care less whether they could display any other character, because even displaying those was a big deal. Nowadays, there are different character formats that are not 8-bit. There are 2-bit or more than that. They're called UTF DAS something, and the DAS says how many extra bits they have. So you can have many different characters, and you can write code that deals with that uniformly. We're not going to deal with that. That's an extra thing. If you want to read about that, do it over the summer. That's a nice thing to know. computers at that day, you had a way of changing the mapping so you could display different, you could do Greek characters if you wanted to by substituting the bit pattern that appears on your screen. So far so good? Okay, so what is the code I'm going to try to write? The code I'm going to try to write is the following. Here's Neosys memory. A location 20, there's going to be the interrupt handler. This is code we have to write. And we'll see how we can write it with the tools we have. In some location, there's going to be our program. This is the user program. And then in some location, there's going to be 1 byte, which we're going to call the character. What will this guy do? So our program is going to be an infinite loop here. What every iteration of the loop will do is we'll take this character. It will go to the transmitter of the UART and say, print this please for me. So to go to the transmitter and say, can I print, can I print, can I print, can I print? Can I send, sorry, can I send, can I send, can I send? The moment the transmitter says send, you're going to write this character. But every time you're going to read it from memory. In the beginning, this is going to be, let's say, the character A. Or let's say the character space, 32. So in the beginning, the value in memory is going to be 32. This iteration will do the following. Read the value, wait until the transmitter is ready, send it out. In the absence of interrupts, I hope you understand that what you're going to see on the screen is a very nice sequence of spaces. You're going to see your cursor doing this, like a terminal. So far, so good? It's just writing one after the other. There is no way this is going to change, because your program is just going to read it and write it. What we're going to do, however, is going to change the UART receiver to say, you know what? Anytime you receive a character, so somebody presses on the keyboard, for example, and they type a new character, raise an interrupt. This routine here will read the character received and will go change this value in memory. So as a result, the moment you press on your host computer some key, you're going to see after that, instead of printing spaces, it's going to print that character. But what's important in this example is that this interaction happens asynchronously with respect to your program. Your program just happily reads this character and writes. In the absence of interrupts, it will write the same thing forever and ever and ever, which means as long as there's power supply. The moment you press some character, the UART receives that, says to the CPU, hi CPU, please handle this. We're going to run the interrupt handler, and it's going to change this value in memory. That's it. Side effect, when you resume execution here, you're going to read the new value and print that. Does that make sense? You understand what the goal is here? Don't think why this is a useful thing. It's useful to illustrate how interrupts work. So let's write this thing. Dot text, dot data, the character, dot byte, and you can write it like that. If you put single quotes and a character in between, your assembler does the job for you. It converts this to the ASCII representation. In this case, it would be as if you wrote the number 32 in decimal, or 0x20 in hexadecimal. Okay. Dot text. Forever. Okay, we're doing the following. We're going to have some initialization code here, where we're going to go to the UART and say, ask for interrupts, whatever. We're going to fill that at the very end. So just put a note there. It's a bunch of constants we have to write to control registers to say both of them, you ask interrupts, you accept them. Okay? We're going to do that at the very end. What we can do now is we can write the code. Okay? We can do movie A, let's say R8, the car. So this is a pointer to where in memory is this byte. Okay. Movie A, R9, let's say 0xFF2000. Was that the UART? You guys remember?
Yes.
I think this is the one. Okay. Now,
Yeah, FF201.
okay. And let's do a send car. We're talking to the transmitter, remember, right? So we have to do what? We have to read the control and status register, go to bit the 16th bit, that is bit 15. So that is 1. Is that the case? Yeah. Check whether that's 1, and then if that's anybody remembers from last lecture what's the setup for the UART? Give me a second, I'll find that.
That's it.
Hmm?
That's correct.
I'm trying to find this on my notes, sorry. It's the upper 16 bits. Okay, I'll remind you. So there's the control and status register. This is a distance plus 4. The upper 16 bits, so 31 down to 16, tell us how many spots are available. So free transmitter slots. So we've got to take that number and see if it's non-zero, then we can send the character. Okay, fair enough? So let's do this. Load word IO, some free register, let's say R10, for R9. So we're in the control and status register. Shift right logical immediate, R10, R10, 16. I hope you recognize this is the code we're writing on Monday, right? So keep the upper 16 bits and fill the zeros on the top, okay? And we say branch equal R10, R0, send car. So we're busy waiting, basically. So there's no interrupts here. We're just busy waiting. That's what we do. Otherwise, what we're going to do now is we do a load byte unsigned. Okay. From the character. Let's do this in R10 again. 0R8. R8, I remind you, is the pointer to the character. So we're reading this byte. Okay. And then we can do a store word IO R10 0 R9. Send it out and keep doing this. So this is an infinite loop. There's this busy wait. Once you are done, you're reading the character from memory. You're writing to the transmit buffer, which is a location 0. It's a write. And then you keep doing this. Fair enough? Just writing characters out. This is the stuff we discussed on Monday. Nothing to it. Now let's deal with the handler.
You need to make sure the top part of R10 stays the same.
Load byte unsigned, 0 extends.
Yeah, but when you store it in the next one, when you store it R9, does it destroy the top half of that?
Yeah, but these are, I mean, the really relevant part, if you look at the definition of the device, is just the last 8 bits. The top are unreserved, we're writing zeros. Okay, that's what the manual says you should do. But it says you should use, I think, for this device, 32-bit writes. Okay, now let's go to the interrupt handler. And for that, I need to remember the syntax a little bit. Now, because this is the interrupt handler, there has to be some specific syntax to the assembler to say that what you're writing is still instructions, but it's actually an interrupt handler, because he has to know that this has to go at location 20. So there is some syntax that is specific to this assembler, and it starts like this: dot section. By the way, you could have said dot section, dot text is equivalent to saying dot text, but dot section, dot exceptions. And then after that, you have to put these things, AX. There are two ways you can approach this index. You can say, this is what it is, I write it down, I don't care. Second one is you can try to understand why whoever designed this linker and assembler has decided to use this syntax. I would suggest you do this over the summer if you wish. I can give you a little bit of information. This means go and put this into the section for this particular device. CPU is used for interrupt handlers. Happens to be 24-hour system. It's a configuration parameter somewhere in some config file for the linker. This means, believe it or not, I means for archival, which really means whatever you're producing, really do store it there. It's like there is actual context there. It's not an information section like a debug or whatever. It has to go into memory. And X means this is going to be code. Execute, that's what it means. What these things mean are specific to every CPU. The toolchain we're using is the GNU bin utils toolchain. That's what it's called, bin utils. They're designed so you can do this for any CPU out there. So this is specific to each one of them. They try to use a uniform syntax, but they don't always succeed because machines are different. So there's only so much value learning this stuff. Okay?
This is immediately after the branch send char, right?
This could be anywhere you want. Anywhere. It's a new section. This is a .text section. This is a .data. You can mix this anywhere you like because the assembler will parse the whole thing and say, this is the image that should create in memory. This means just go start the duplication 20. And now what? So handler. Now, for this example, to start with, I'm going to assume, or actually I'm not going to assume, I'm going to configure the whole system so that there is only one device that can ask for interrupts. So my first version of the code is not going to say, is it really the UART that's asking for interrupts? It's going to assume that that's what it is because that's what we're going to configure the code to be. Later on, there are actually code examples in the notes too. You can have a handler that says, oh, I got a call from somebody. There are 32 devices. Which one was it? So there's going to be some code in the beginning that says, was it you? Was it you? Was it you? Who was it? Here, we don't have to do that because by design for the code, we're going to configure there's only one. So we can skip those details. Okay. Now, what we're going to do, we need a pointer to the device. I'm going to try, no, I'm going to use, I'm not going to try. I'm going to use a different set of registers so these two programs don't mix with one another, so I don't have to save anything on the stack. This is, again, so for expediency. That's not how you write this stuff. R4, 0xFF20,000. This happens to be the same as that constant, but remember, this is meant to be an interrupt handler. It could have been anything, and this could have been anything else. Now, this is the receiver. Because it's an interrupt, we don't have to ask the receiver, do you have a character? The only reason this is going to get called is when there is a character. So we don't have to interrogate and say, do you have? We don't have to ask. We know that's a given. That's how we're going to configure things. So what we're going to do is we're going to go to it and say, load word IO R2 0 R4. So now this reads the receive buffer. And recall that bit 15, the 16th bit, is 1 if there is a character there. We don't have to check that. We know this for a fact because that's the only reason why this is going to get called. All we got to do is we got to extract the character. So and I R2 0xFF. And this may even be superfluous because we're going to do a store byte after that, so I don't think we even need that. But let's put it there. And then we can do a store by, movie A, R4, 0x, the car, which by the way is the address where this byte is in memory. And I should have written it with the appropriate case. And now we can do a store byte R2, 0, R4. Okay. Ta-da. And now we go to add I, EA minus 4. Remember, we had a long discussion on why we have to decrement EA. And then we say IRIT. That's it. Here. We're cutting a lot of corners here because we do know what this code is, so it's always a different set of registers here. We're not asking the device, were you the one that asked, because we're going to set up the code so that it's that device that asks. We can fix this later on, right? So this is meant to illustrate that. This part is going to be pretty much common to all interrupt handlers. That part is specific to every device. Now, if you write this code and you try to run it on your board, nothing's going to happen. Why? Because you have to say to the device, you please ask interrupts when you receive characters, and you have to say to Neos, please accept interrupts from this guy. And that's where it's going to go here. So we have to set up a bunch of registers to do that. And we have 5 minutes to do this. Okay. So there are two parties involved in this communication. One is the processor. So we got to tell the processor, listen to this device. And the other is we have to say to the UART, please ask for interrupts. Okay? UART, how do we make the UART ask for things? So the UART, it has the control and status register. This is the UART side. 31 down to 0. And if I remember correctly, oh, that's in my previous notes. Wonderful. Give me a second. I got to extract this from the constant. Blah, 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 blah. Dee, 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 dee. That's not good. Sorry. My apologies for this. I should have remembered this from the top of my head. Aha, found it. Sorry. No, I didn't find it. Sorry, this is very embarrassing now. But I think it's bit 0, but I don't know why I cannot find this. Anybody has the notes from last time? That's very nice for me to be asking now 5 minutes before the lecture.
It's ERI or EWI?
It's received, ERI. It's bit 1.
So that's 0.
Bit 0. Okay, thank you for that. So these are two switches, ERI, and this is the EWI, right?
Yep.
All right, sorry for that. And it's going to be on YouTube forever. Okay, good. These are switches. When you write to this register, you can change the values for those. 0 means the switch is off. 1 means the switch is on. So what we got to do is we got to go and write 1 there. This means to the UART, anytime you receive a character, go and assert the IRQ line. Ask for an interrupt from the CPU. Okay? So the UART then immediately will start knocking on the door for the CPU anytime there is a character. That's one of the parties. The others, you have to say to the CPU, accept interrupts. So CPU actually has 2 fortifications. It's like there is the royalty, which is the CPU sitting up on the throne, and there are 2 sets of guardians that you have to go through. Right? There is the individual per device, per wire, and then there is the main, like the, how do you call this? The boss at the end, okay? So CTL 0 is the boss. This is interrupt enable. And this is bit 0. If this is 0, CPU will not accept requests from anybody. This is the last person you got to go through before you go to the CPU. And then there is CTL 3, which has 31 bits. Each one of them is a switch. This is for IRQ 0. This is for IRQ 31. And the one we care about is for IRQ 8, because in our board, that's the UART. So the UART is connected to physical line IRQ 8. We got to set this bit to 1 and that bit to 1 so that the request can be allowed to go to the CPU and the CPU will accept it. If any of those are not 1, the CPU is not listening. Okay. It's 3 o'clock. Sorry for cutting this short today. We're going to do the constants tomorrow rather than me rushing in a few seconds to tell you what it is. But it's going to amount to the following. One store word to this location. So we set that bit. And then there are specific instructions. One is called write control register. The other is called read control register. 2 write control registers, 1 to 3 to enable interrupts for RQ8, and 1 to 0 to enable interrupts for everybody. Okay, that's the idea behind it. It's in the notes, but we're going to do it tomorrow, right? Okay, good. So thank you for your patience today, and I'll see you tomorrow then.